Okay, so our final speaker is Rob Knowles from Princeton University. So Rob did his undergraduate degree at I'm forgetting the school. Why am I forgetting the school? Well, that's not really good.
William and Mary.
At William and Mary, and he worked with Rob Hinkle, who's a fantastic undergraduate mentor. So hopefully he really sort of fired you up into chemistry. And then you went to do your PhD with Dave McMillan at Caltech, and I hope he didn't burn you out too much after Rob Hinkle, but obviously he didn't. And then you went on to do a postdoc with Eric Jacobson, and then came back to Harvard, came back from Harvard to Princeton in 2010. And so one of the ways you know that someone is doing well, okay, they get awards, and definitely Rob has got many, many awards. But one way that you know people is doing really well is they start off, of course, as an assistant professor. And then after that, you're supposed to become an associate professor. Well, I'm sorry to say that Rob failed to become an associate professor because he got promoted immediately to full professor after 6 years, which is really pretty amazing. So really congratulations on all the wonderful work you've done. And you'll see that his program has got a really interesting sort of ideas in terms of thinking about developing new reactivity, a lot of electron transfer, proton transfer work. And the title of today's talk is Light-Driven Deracemization. So Rob, welcome. We're really looking forward to your presentation.
Great. Thanks, Hugh. Thanks very much for the kind introduction. Let me get my slides here. Let's see, does that show up okay?
Yeah, it looks great.
Super. So thanks again, Hugh, for the very kind introduction, and thanks to the CCHF for the invitation to be here this afternoon. I'm really excited to have a chance to share with you a kind of maybe unusual story about CH functionalization that's primarily stereochemical in nature, and trying to develop methods to enantioselectively break and reform stereogenic CH bonds in the context of developing methods for light-driven deracemization. And this is a project that we've done in collaboration with Scott Miller's group at Yale. So just by way of background, deracemizations are a somewhat unconventional class of asymmetric synthesis, wherein a racemic mixture of a given compound is wholly transformed into a single enantiomer of exactly the same compound. And despite being, conceptually simple and having some potential practical benefits, the development of catalytic deracemization chemistry remains relatively rare. Now, there's a number of reasons why that is, but fundamentally, these types of reactions face sort of two really significant energetic challenges. First of all, on thermodynamic grounds, deracemization is just fundamentally unfavorable. So in terms of the free energy of these reactions, you're converting a two-state system into a one-state system. And as a result, there's an attendant entropic penalty. And this penalty is relatively small. It's just around a half a kcal per mole at room temperature. But nonetheless, this requires that you have some sort of exogenous driving force that you have to add to the reaction to be able to sort of push this reaction against this sort of thermodynamic bias. Now, there's lots of ways that we could imagine coupling this to some sort of energy source. And it turns out that the much more difficult energetic challenge is actually kinetic in nature and relates to the principle of microscopic reversibility. So since enantiomers are equal in energy by definition with respect to on a potential energy surface, any series of elementary steps that are able to interconvert between, say, R and S enantiomers are going to be equally accessible in both the forward and the reverse directions. And so as a result, the system is able to access all the states along the potential surface, which is the condition for being at equilibrium, which in this case turns out to be racemate. So in order to overcome these microscopic reversibility constraints, what we really need to be able to do is to sort of introduce an energetic bias. We need to sort of tilt this energetic landscape such that all the elementary steps that sort of convert the two enantiomers are all favorable and all proceed in sort of thermodynamically downhill in irreversible fashion. But if you really think about that, if you imagine that these steps are all going to be favorable, what that implies chemically is that the steps that create and destroy stereochemistry, those specific elementary steps, have to be mechanistically distinct. Now, this is a subtle point, but I think a really important one. And this is, I think, a very, very significant challenge associated with designing deracemization chemistries, is you have to be able to break and reform stereogenic CH bonds in the same catalytic cycle, but do so through two distinct mechanistic events. And so the ways that people have traditionally tried to address this challenge is by using combinations of chemically compatible oxidants and reductants that can function together in the same reaction vessel to provide the thermodynamic driving force, but which together create and destroy some sort of common achiral intermediate. So just to give you some examples of some of these types of methods, many of them are biocatalytic in nature, and one of the real pioneers in this area was Nick Turner and his group at Manchester. And I show you here just an example of an amine deracemization from the early 2000s, where the Turner group was able to evolve an amine oxidase, which can aerobically oxidize just one enantiomer of a racemic amine substrate to the corresponding imine, and leaving behind the slower reacting enantiomer, which builds up and optically enriches in solution. Now, these reactions can be conducted in the presence of these amine-borane reductants, which can non-selectively reduce the imine that's formed to regenerate a racemic mixture of amine, which can then be processed through the cycle iteratively. And ultimately, repeating this many times, you're able to generate a reasonably good material throughput and very, very high optical purity of these deracemized amine products. So, as I mentioned, most of the work in this area has been biocatalytic in nature. In terms of small molecule asymmetric catalysis, the number of deracemization methods that have been developed is quite a bit smaller. In fact, they're really just a handful. And I show you one of my particular favorites from Dean Toss' group in 2013, where they're able to deracemize these indolene derivatives, again using combinations of oxidants and reductants in the same reaction vessel. But in this case, these two hydride acceptors, this oxoammonium and Honchester, are not chemically compatible. And they actually have to be sort of partitioned into separate phases. And this is a triphasic mixture of aqueous, organic, and solid phase. And then use phase transfer catalysts to be able to ferry reagents and starting materials between the different phases to drive the deracemization process. So a really, really creative and sort of unique solution to this particular challenge in reaction design. But I think in thinking prospectively about sort of developing these methods more broadly, this approach to chemically driven deracemization presents some sort of obvious types of challenges. So fundamentally, deracemizations are redox neutral processes. But in this case, we're requiring sort of multiple equivalents of multiple stoichiometric reagents to be able to drive these reactions forward. Moreover, this sort of challenge associated with chemical compatibility also can be challenging to meet and present some challenges associated with generalizing these types of methods. So, in considering all sorts of alternative approaches to developing deracemization chemistry, one attractive approach is to photochemical types of methods. And the photochemistry community has discussed and written about developing light-driven deracemization methods now for a number of decades. But the very, very first highly enantioselective catalytic deracemization that was light-driven was reported just about 18 months ago by Torsten Bach's group in Munich. And this is a really, really phenomenal paper. And in this work, the Bach group was able to deracemize these chiral allyne substrates using these lactam-based hydrogen bonding catalysts that they've developed over the past several years. So in these reactions, these lactam-based hydrogen bond catalysts form strong associations with only one of the two enantiomers of the substrate. And the resulting hydrogen bond complex can undergo excitation and sort of a pseudo-intramolecular energy transfer to transfer that excitation to the bound allyne substrate. It turns out in the triplet states, allynes undergo planarization and they lose their stereochemistry. And these planarized allynes can then relax back down non-selectively to regenerate sort of the racemic allyne starting material. So this reaction slowly becomes enriched in the enantiomer that's unable to undergo this energy transfer with the lactam catalyst. And repetitively in consuming a photon for each cycle, they're able to get very, very good mass recovery and very, very high levels of optical enrichment. So this is an absolutely phenomenal result, and I think a culmination of a long-standing goal and sort of the organic photochemistry community. But this particular approach does require, to be able to do these energy transfer types of deracemizations, that you have substrates that have energetically accessible excited states. And so in considering other ways that we could think about using photochemical approaches to drive these deracemization reactions, our group became particularly interested in the prospect of doing this using excited state electron transfer events instead. And so just to walk you through our particular approach to this, you could imagine that you have some sort of catalyst or chromophore that's able to absorb a photon to generate an electronic excited state that will have augmented redox properties. And this excited state is then able to engage in some sort of excited state electron transfer with a substrate of interest to generate this sort of key charge separated intermediate. And this key charge separated intermediate, you can see, of course, is much higher in energy than the corresponding starting materials, reflecting the fact that it's been able to sort of capture some of the energy associated with that initial photoexcitation event. Now, the key aspect of this is, if you consider all the pathways that are able to consume this key charge separated state, whether it be simple back electron transfer, where the electron and the hole recombine to be able to push the system back towards the starting material, or if this charge separated state undergoes some sort of productive reaction to lead to, say, the desired product B in this case. All of these pathways are thermodynamically favorable relative to the charge separated state. And the partitioning between them is completely under kinetic control. It's just a function of the differences in the activation energies of the various pathways leading away from this key intermediate. And as such, the partitioning is completely decoupled from the ground state thermochemistries of A and B. So we can use this reaction or use this type of manifold to be able to drive these reactions away from equilibrium and generate populations of sort of the higher energy product. Now, I won't claim to you that this is any sort of novel insight. This is the way that photosynthesis works in green plants. And this is the sort of intellectual blueprint, I think, of much of the solar fuels chemistry that's been developed in the inorganic community over the past few decades for small molecule activation. But our group has really become interested in these types of redox approaches to driving reactions out of equilibrium in the context of organic synthesis in recent years. And this will play sort of a key role in the deracemization story that I'll tell you on the next few slides. So it turns out that our sort of forays into deracemization chemistry began somewhat serendipitously. And we were actually attempting to develop an enantioselective hydroamination method based on some of our prior work in so-called proton-coupled electron transfer reactions. And in this reaction, what we hoped to have happen was to have a chiral phosphate base, a binol-based phosphate that could form a hydrogen-bonded complex to this amide substrate, activating it for oxidation by the excited state of this iridium chromophore. And that would result in a PCT event that would oxidize this NH bond, leaving behind a neutral amidyl radical that could cyclize onto this alkene to form the desired heterocyclic product. And what we hoped is that the conjugate acid of the chiral base that was formed in that PCT event would be able to maintain some sort of non-covalent association with the nascent radical that's formed and be able to sort of direct the stereochemical outcome of that CN non-forming step. So the postdoc who was working on this project started to sort of realize experimentally some quite low but non-zero levels of enantioselectivity. When we looked at this reaction further, it turned out that it was very, very oddly behaved. The reactions were very irreproducible, and they seemed to vary strangely as a sort of a function of reaction time. And ultimately, what Mark was able to show is that these reactions are essentially completely racemic until all of the starting material has been consumed. And as soon as the reactions reach completion, the optical purity of the product slowly begins to rise. And to sort of demonstrate this more clearly, what Mark did was to take the racemic product of this reaction and then to resubject it to the reaction conditions. And sure enough, after a few hours at room temperature under blue light irradiation, we're able to sort of recover almost a complete mass balance of now quite substantially optically enriched materials. This is clearly not consistent with any sort of kinetic resolution. It seems that we're accessing some sort of light-driven deracemization type of pathway. So with respect to how we might imagine a reaction like this would work, our sort of postulated mechanism is shown here. So in these reactions, what we can show is that these the product of the hydroamination, this aryl urea compound, is readily oxidized by the excited state of the iridium chromophore that we employ to generate the sort of corresponding radical cation intermediate. Now in these radical cations, these adjacent CH bonds become very dramatically acidified to the point where they can actually be favorably deprotonated by very, very weak bronze step bases, which in this case, these phosphate anions, to generate these, effectively achiral, rapidly equilibrating alpha amino radical intermediates. Now, these electron transfer events are non-selective. So if we begin with a racemic mixture of the starting material, we'll generate a racemic population of these sort of radical cation intermediates. However, their interactions of each enantiomer with a homochiral phosphate base will be diastereomeric in nature. And essentially, we can affect a kinetic resolution of these radical cation species. So one of the radical cations will undergo a comparatively fast deprotonation, and that stereochemistry will be destroyed and converted to the sort of achiral alpha amino radical intermediate. While the slower reacting enantiomer can undergo charge recombination with the reduced form of the iridium-2 photocatalyst. So the reduced iridium-2 species gives an electron back to this radical cation faster than it can be deprotonated, pushing it back towards the starting material, but importantly retaining that stereogenic center. So the reaction will become slowly enriched in the isomer that's unable to undergo deprotonation from its radical cation intermediate. The resulting alpha amino radical can then be non-selectively reduced by the achiral thiol co-catalyst to regenerate racemate, which can then recycle through the mechanism again. Now, in thinking about this, there were a number of features of this particular mechanism that we thought were attractive. And the first one is it sort of met those requirements that I laid out at the outset. All of the elementary steps from that initial iridium excited state are favorable. So the series of electron, proton, and hydrogen atom transfer steps all proceed irreversibly and sort of downhill in energy as we would like them to. But perhaps more importantly, the mechanisms for the elementary steps that create and destroy the CH bonds are distinct in this case. So we have destroy CH stereochemistry using a proton transfer event and reform it using a hydrogen atom transfer event. And so not only are these two elementary steps mechanistically distinct, but they're actually mediated by two completely independent catalysts. And so we became interested in the prospects. Could we actually render both of these steps enantioselective if we were able to say also identify a chiral thiol that could mediate an enantioselective hydrogen atom transfer event? Now, if you think about this is kind of an unusual scenario where you actually have two sequential enantioselective steps that occur in sequence within the same catalytic cycle. And if you sort of work through the math on this, if you assume that back electron transfer step is faster than deprotonation, you can arrive at a rate expression that has a really unusual form. That in this case, in this mechanism, the overall level of optical purity that you would observe would actually be the product of the enantioselectivities for each of the two independent elementary steps. So you could imagine in this case, if you've got the enantioselectivity for the proton transfer step, would actually multiply times the enantioselectivity we observed for the hydrogen atom transfer step. We thought not only is this a pretty unusual outcome, but it also potentially could be really beneficial. Right? You could imagine having two processes that are relatively lowly selective in and of themselves, but so long as they operate in sort of a stereochemically matched manner, we should be able to overall generate much, much higher levels of enantioselectivity. So we thought this was a really sort of interesting and unique feature of this particular mechanism. And we decided to see if we could sort of realize this experimentally. So at this point, we reached out to Scott Miller's group at Yale and began a collaboration. And I'm sure many of you or all of you are familiar with Scott's many wonderful contributions over the years and using these sort of polypeptide-based organocatalysts. But recently, Scott's group has become interested in these cysteine-bearing variants that we thought potentially could have a role as enantioselective hydrogen atom transfer catalysts in this chemistry. So what we hope to be able to do was to identify sequences of polypeptides that could serve as enantioselective HAT catalysts and identify chiral bronze-dead bases that could act as proton transfer catalysts and try to affect the deracemization of these cyclic urea types of substrates. And in particular, we were really interested if we could observe this sort of amplified enantioselectivity, where the observed levels of stereoselectivity would be the product of the two independent elementary steps. So Nick Shin in my group and John Reese and Scott's group set out to sort of reduce this idea to practice. So what we did in this, to prosecute this idea, was to optimize the two catalyst structures independently of one another. So in this case, we would optimize the structure of the chiral base using an achiral thiol, so that any enantioselectivity that we would observe in these reactions could solely be attributed to the action of the chiral proton acceptor. So in this case, we screened through a variety of chiral binyl phosphate bases, and ultimately we were able to arrive at this pyrene substituted phosphate, which gave reasonable mass recovery and pretty significant optical enrichment, around 6:1 ER, not incredibly high, but certainly noteworthy. So we're using this as our proton transfer catalyst. At the same time, we tried to optimize the structure of the chiral peptide. In this case, we used an achiral phosphate as our proton transfer catalyst. So again, that all of the enantioselectivity that we would observe here could be solely attributed to the action of the chiral HAT reagent. And after screening through a number of sequences, we were able to arrive at this particular sequence bearing this phenylglycine derivative. That again gave a reasonably modest stereoselectivity for that for the enantioselective hydrogen atom transfer step, around 4:1 ER. So really the key sort of question in the project was, if we were to use the sort of stereochemically matched forms of both of these catalysts, could we observe this sort of multiplied level of enantioselectivity? So we have around a 6:1 selectivity and a 4:1 selectivity. If these two things are able to operate in our mechanism independently in that same catalytic cycle, would overall the selectivity we observed here be around 24:1 selectivity? And we were really gratified when we actually were able to run this experiment, that sure enough, if we take this aryl urea derivative that has this pinned at amide, we believe this has a hydrogen bonding interaction with the phosphate that helps to drive the proton transfer step. But we irradiate this in room temperature THF, and after a few hours, we can generate essentially a complete mass recovery. 98% of the material is returned. That's now very, very highly optically enriched. In fact, this optical enrichment exactly matches that we predicted based on the model of these two catalysts acting independently in this cycle. Sure enough, if we use the antipode of the chiral thiol, so we use the mismatched form of the hydrogen atom transfer catalyst, now we still get good mass recovery, but now the observed enantioselectivity is essentially racemic, again, sort of suggesting that the stereochemical preferences for creating and destroying the CH bonds in this mismatched form are sort of acting in opposition to each other and leading to diminished stereoselectivity, again, consistent with our model. So with these catalysts in hand, we looked a little bit at some of the substrate scope of this reaction, and I won't belabor this in any sort of a meaningful way, except to say that you can vary various positions around these substrates and still maintain reasonably high levels of mass recovery and optical enrichment. But one thing that I think this did allow us to do was really to sort of address the question, is this sort of amplified levels of stereoselectivity a general feature of this particular transformation, or did we really just get lucky with the model substrate that we initially evaluated? So what we did next, or what Nick did next, was to basically take a subset of the substrates for the method, and then we could actually then evaluate the enantioselectivities for each of the two independent elementary steps alone. So again, we could measure just the enantioselectivity of the proton transfer step using the chiral phosphate and an achiral thiol. You can see those values are reported here and vary over a reasonably wide range of selectivities. We could then do the sort of opposite experiment, where we would use this chiral thiol and an achiral phosphate base and evaluate just the enantioselectivity of the hydrogen atom transfer step. And based on these values, we could predict the observed level of optical enrichment that we would use if we had these sort of two catalysts operating together in the same catalytic cycle. And we were really gratified to see that across the board for all the substrates that we evaluated, the observed experimental levels of enantioselectivity more or less exactly matched those that were predicted, typically within an ER point or two. And the mass balances in all cases were extremely high, typically above 90% yield. So with this in hand, we can sort of start to think about some other neat things you might be able to do with this type of chemistry. One is that thing that we're able to demonstrate is a catalyst-controlled enantiomerization. So we can start with one enantiomer of the substrate, convert it all the way down to racemate, and then bring it out the other side and convert it with very, very high yield and selectivity into its corresponding antipode. Now, one could argue, right, that I think this is a nice sort of little trick, but I think that, doing these types of stereo inversions or stereo permutations with molecules that have a single stereogenic center is interesting, but perhaps maybe not that useful. What we really think is sort of the future in thinking about this type of chemistry and how we hope to be able to sort of push this forward in a perspective way. I think I can show you in the next figure here. And this is hypothetical work. This isn't work that we've yet accomplished, but what we're really hoping to be able to do is to develop distinct pairs of catalysts that are able to selectively address different types of common stereogenic centers. So ideally, we could come up with catalyst sets that would be able to sort of specifically deracemize or epimerize alpha carbonyl stereocenters or alpha oxy, alpha amino, or benzylic. And if we could do that selectively, what this would allow us to do, I think, would have a sort of a very unique approach to thinking about stereoselective synthesis. So imagine if you had, say, a lead compound in a medchem series that you wanted to make all the different possible stereoisomers. Traditionally, right, we would have to come up with sort of a distinct stereoselective synthesis for all of the different isomers that we'd like to be able to make. In this model, if we could achieve it, right, one could start with just a single pool of material that may even be stereo-random, and then be able to use catalysts to be able to selectively epimerize or selectively isomerize specific stereogenic centers within that substrate to be able to access all the potential stereoisomers in a catalyst-controlled way that's not subject to sort of equilibrium thermodynamics. And I think this would be a sort of quite a distinct way of thinking about stereoselective synthesis that I think potentially has some really interesting practical benefits. So this is where we really think the sort of future of this type of chemistry might lie. So with that, I will close. I'd like to thank the folks who actually did all the work here. So Nick and John did the bulk of the sort of substrate scope and mechanistic work and catalyst development that I showed you. Mark was a postdoc who initially observed deracemization behavior in the hydroamination chemistry. I'd also like to thank Scott. This has been a really, really fantastic collaboration and lots of fun for our group, and we're continuing to work together, and I've really enjoyed working with Scott and his students. I'd like to thank the rest of my group, and also like to thank all the folks who support our research program, and I'd like to thank all of the audience for sticking around until the end, and I'd be more than happy to answer any questions.
Okay, Rob, thanks very much for a great talk. And let's see if people remember how to do an appropriate round of applause at this stage. Wow, it's great to see the level of enthusiasm is still high at this time of evening. Okay, so we got some questions for you, Rob. So a question from Donna Blackman. Hi, Rob, great talk. Is this amplification like an RO expansion?
Hi, yeah. Hi, Donna. That's a great question. I think that's a really good analogy. I think that's how we sort of think about it as well in terms of this sort of multiplied stereoselectivity. I think it's a little bit different in some ways too. I think these systems are perhaps also thought of accurately as being more like photostationary states. And really that the sort of equilibrium EE that you observe is really the relative the ratios of which the enantiomers are created and destroyed. And so you can sort of derive expressions that sort of reflect that. But it really, I think, is the systems importantly are dynamic. They're not, doesn't sort of just proceed to product and then, in a normal way. if you were to say add in deuterium or add in an achiral catalyst, the systems are still able to sort of adapt and undergo further transformation. So the catalyst system is living. So it is a little bit different, I think, but I think that Hero analogy is really, really apt and something that we've sort of drawn inspiration from.
So Rob, people are getting out of control with your talk. There's still hearts and thumbs up coming like crazy. I don't know.
Thank you.
So a question from Olivia Langer. Thank you for this fascinating presentation. Have you considered also under mediator electrochemistry to selectively oxidize or reduce one enantiomer for enrichment similar to what you've seen via photochemistry?
Huh, yeah, thanks. That's a really interesting question. You know, we have not looked at that in any sort of detail or thought about that, but I think that's a really interesting approach and definitely worth thinking about. So thanks for that suggestion. It's definitely something to think about going forward.
Okay, Joshua Newton just wants to tell you thanks for a great talk. He's probably still putting those thumbs up like crazy as we're still going on. We have a question from Xiaotan Ji. A great talk, Robert. Can you talk more about the entropy effect shown at the beginning?
Sure. You know, I think one way to think about this is essentially almost like an entropy of mixing problem, right? So the important distinction, I think, between the two slides that I showed on sort of the thermodynamic and kinetic challenges is that the thermodynamic ones here reflect the sort of free energy of the system. So they're Boltzmann weighted. They sort of take into account these entropic contributions. And so taking a racemic mixture that's formerly a two-state system and converting it solely into a one-state system, it's a single enantiomer, there's essentially a loss of entropy associated with sort of the number of configurations that the system can adopt. And so I think you can think about that in some sense as just the sort of R log 2 Boltzmann type expressions, though I think there is some more sort of subtlety to it. But I think that's how we would sort of approach it. I think it's interesting to sort of think about, you know, what is the driving force for racemization, right? We oftentimes think if we have, say, you know, stereochemically labile CH bonds, say alpha carbonyl CH bonds, they'll readily racemize under the action of base. The thermodynamic driving force for going from a single enantiomer to a racemate is essentially, again, this sort of increase in entropy, because enthalpically the enantiomers, of course, by definition, are equal. So that's I think the way that we think about this. But I hope that answers the question.
Okay, so now we've got an interesting question from an anonymous attendee. Great talk, Robert. Have you considered to induce multiple stereocenters?
Yeah, that's something we'd love to do, and also trying to sort of expand the types of functional groups and CH bonds that we can sort of use in this manifold to things that are a little bit more and less contrived in the substrates that we initially developed. So that's something that's definitely sort of we're looking forward to in the future.
Okay, and then one final question from Grace Panetti. Awesome chemistry. Where do you think the benefits and detriments of charge transfer versus energy transfer in these deracemization reactions?
That's a great question. You know, so I mean, the Bach group has, I showed you the one example, but they've also expanded this to other types of substrates as well, and have done a lot of really nice work recently in this space. I think the big difference is just, you know, the types of substrates that will work in one manifold versus the other. You know, to be able to sort of do energy transfer, you need to have an energetically accessible excited state. And I think especially for, you know, if we want to stay in the visible or close to the visible, there's going to be a somewhat limited sort of collection of functional groups and chromophores that are able to sort of engage in that type of energy transfer chemistry. On the electron transfer side, I think the big difference is really you're potential gated. You're just limited by what types of species you can oxidize and reduce to sort of get into the cycle. But I think the key point is that both of these excited state manifolds sort of operate across two distinct potential energy surfaces. And so as a result, they're able to sort of overcome the sort of detailed balance arguments that really sort of preclude doing this or typically preclude it doing this in a thermal way. So I think they're not certainly one's better than the other. They're just complementary in the types of substrates that they can activate.
Okay, great. Well, Rob, thank you very much for a wonderful talk. And also thanks to all the other speakers. Ang Lee, thank you for staying with us throughout the whole session. Pedro left us, I'm sorry to say, but he had a really good excuse because apparently they were going to lock the gates of the university if he didn't get out in a certain time. So that's a reasonable excuse for not to listen to every talk. But all three speakers gave fantastic presentations, really shows a lot of variation how one can think about CH functionalization, and just shows the field will continue to develop as long as people show this type of innovation and the way to use the chemistry going forward. So once again, thank you very much. Great presentations. I'd also want to thank Rio and Denise for doing a fantastic job. Rio in particularly because he ran a very smooth program, and he probably will kill me for saying this, and this was after some serious dental work, so really sort of sacrificing his body to run this session. So thanks very much, Rio. So anyway, great session all around, and hope you'll join us in the next meetings that'll be coming up soon. Look out for the schedule. Okay, bye now, everyone.
All right, thank you.